this video, we will be discussing about minimum number of operations to sort a binary tree by level. You are given the root of a binary tree with unique values. In one operation, you can choose any two nodes at the same level and swap their values. Return the minimum number of operations needed to make the values at each level sorted in a strictly increasing order. So what they are saying is that in the input, we are given the root of a binary tree. Now, what we need to do is that we need to sort all the values which are present at a particular level, at the same level. And all the values in our binary tree are unique. This is also given to us in the question, right? So now, what is a level? So a level of a node is nothing but the number of edges along the path from the root till that node. So if you see, this is the root. If I try to find out the level of this node, so we have two edges in the path, right? So the level of this node will be 2, right? So this is level 0, this is level 1, this is level 2, and this is level 3, right? So whatever nodes are at the same level, we need to sort them in strictly increasing order. And for that, in one operation, we can swap any two nodes at the same level, right? So we need to return that how many minimum number of swaps are required to make the values at each level in the binary tree sorted in strictly increasing order, right? So in this level, we are having only one node, so this is already sorted. Then in the next level, we have 4 and 3, right? This is not sorted, so we will have to swap. So there's only one option that we can swap the values of 4 and 3. So 3 will come here and 4 will go here, right? So this is one swap that we perform, right? One swap. Then we come here. Now here we are having 7, 6, 8 and 5, right? This is not sorted, right? For sorting this, what you can do first, you can swap 7 and 5. So this will come as 5, 6, 8, 7, and then you can swap these two. So it will be 5, 6, 7, 8. So total 2 swaps were required for this level, right? And then these two are already sorted. So the total of these is 3. So your answer is going to be 3 in this particular case, right? So now, since we want to sort the values at each level, obviously we would be needing all the nodes which are present at the same level, right? So this gives us a hint of applying BFS over here, because BFS traverses level by level in a binary tree, right? What do we do in a BFS? That in a queue, we take a queue, right? In that queue, we insert the root node initially. So if this is my queue, then we insert our root node initially, and then we run a loop that while this queue does not becomes empty, we take the size of our queue, currently whatever it is, and then we run a for loop this size many times, right? So right now its size is only 1, so our for loop will run only once, right? In that we will pop this out, right? So once you will pop this out, whatever are its left and right child, that we push back into the queue, so that when we move into the next iteration, we have the next set of nodes. Basically, in the next level, whatever are the nodes that will be present in the queue, right? So that for loop is going to run once. This one will come out. You will have a node 1, right? And then you can push its left and right child into the queue. So 4 and 3 would be inserted here. And then whatever are the nodes that you are taking out from the queue, you can store them in some vector, right? And then you can identify the logic of identifying that how many swaps are required to sort that vector, right? So this one is already sorted, there's no need. So our for loop will be finished now, right? So now it will again check, is the queue empty? No, it is not. We are having the next level's nodes inside our queue, right? So this is 2, right? The size of the queue is 2. So for loop will run 2 times, right? First it will take out 4, right? So you will get a 4. You can insert that, or you can push that into some vector or some array, right? And then whatever are its left and right child, that you push inside the queue, right? And then in the next iteration, you take this 3 out, right? So that is also inserted in this array. So once that loop has run 2 times, you have got all the nodes at this particular level inside that vector. Now you can identify that how many swaps are required in sorting this. So only one swap, right? So in some variable, maybe total swaps, you can make its count as 1, right? And when you took out this 3, you would have also pushed its left and right child into the queue, right? So 8 and 5 will come here, right? So now when we are done with this will be removed. Our vector will be recreated again for the next level, right? So again it will check, is the queue empty? No. What is its size? 4. So there will be a for loop which will be running 4 times, right? In the first iteration, it will take 7 out, right? And it will push its left and right child, but we are not having any, so it won't push anything. In the next iteration, it will take 6 out. Again, 6 is not having any left and right child. So in the next iteration, it will take 8 out, right? Now there is one child of 8, which is 9. So 9 will be pushed here, and then it will take 5 out. So 5 will come here, and the child of 5, that is 10, will be pushed here. So now our for loop has run 4 times and we have got all the nodes. Again, we can identify that how many swaps are required for sorting this array, right? And that you will get as 2, right? So your count will become 3, right? Again, we'll move for the next level. So in that, first we will take out this 9. 9 will come here, and then it will push its child, but we are not having any childs, so then it will take out this 10. So 10 will come here. It is not having any childs. Our loop has run 2 times, so it will stop now, right? Now we'll see how many swaps are required here. So 0 swaps, right? So this count will remain as is, and then this will be removed. We will move on to the next iteration. Now it will see that the queue has become empty, so it will stop. And in our count, we are having how many swaps are required, right? Now the only problem left to solve is how to identify that how many swaps are required to sort an array or a vector, right? So let's look into that. So if let us suppose that I have an array 5, 3, 2, 1, 4. Let us suppose this is the array in which I need to find out that how many swaps are required, right? So let me give the indices. This is 0, 1, 2, 3, 4, right? Now, what is this array going to look like when it is sorted? So 1 will come here, 2 will come here, 3 will be here, 4, 5, right? And this is our 0, 1, 2, 3, 4, right? Now, with the help of the sorted array, I can identify that where the values are not matching, right? So if you see, if we look at the index 0 in both the arrays, so ideally there should have been a 1 present over here, but it is not. 5 is present. Then that means a swap is required, right? But with which element are you going to swap this index? Obviously, wherever 1 is present, right? So we will swap 0th index and 3rd index. So 1 will come here and 5 will go there, right? And your number of swaps are 1, right? Then you will check for the next set of elements. Now here 2 should have been present, but 3 is present, right? So we will swap it with index where 2 is present. So 2 is present here, right? So we will swap these two. So this will become 2, 3, and the swaps will become 2. Then you will check these. Now these are matching. Then we'll check these two. These are not matching. At index 3, 4 should have been present, right? So we will find where 4 is present. So it is present at index 4. So we will swap these two indices, right? So 4 will come here, 5 will go here. Number of swaps will be increased by 1. Then these are matching, and then we are done with the array. Our array sorted. It required 3 swaps to sort our array, right? So with this, we will be able to identify. But now, if we move back to the unsorted version of the array, so here, these values are not matching, right? So a swap is required, and a swap is required with an index wherever 1 is present, right? Now, how are you going to identify that at which index 1 is present? So for that purpose, what we can do is that we can maintain a map, right? We can maintain a map, and in that map, we can store the indices of all our values, right? In our tree, the values are always unique, right? So in the map corresponding to each node value, we can store its index, right? So here the values are 1, 2, 3, 4, 5, right? So in the values, you will store their indices. So 1 is present at index 3, so we will store 3 over here. 2 is present at index 2, 3 is present at index 1, 4 is present at index 4, and 5 is present at index 0, right? Now what we can do is that we can run a loop for all these elements, right? So basically you would be running a for loop of I from 0 till whatever are the number of elements in your array right now. Let me denote it with n, right? So now I will check that if, so this, let's suppose this is our original array and this is our target array. So if at any point the element in original, that is original of I, that is not equals to target of I, then that means a swap is required, right? So whenever a swap is required, we will increment our number of swaps count by 1, right? And then we need to swap those elements after identifying the index from the map. right? So see, when these two are not matching, so we need to swap this with the index wherever 1 is present, right? So from the map, I will identify what is the index of 1. So it is 3, right? So then that means I need to swap the index I with this particular index, right? So if I denote it with current position, so int current position will be equals to, if let's suppose the name of the map is positions, POS, right? So you'll write position of target of I, right? So basically, whatever is present in the target at the current index, that is 1. From the map, we are identifying what is its index. So its index is 3. This 3 will come in this current position, right? So now we need to swap index 0, that is index I, and this index, right? Now, when we are swapping these, their positions will change after swap, right? So we also need to update the new positions in the map, right? So when I'm swapping index 0 with 3, now the index of 5 will become 3. Here it is 0, right? So we will update it to 3. Now, do we need to update the index of 1 as well? See, once we are done with this, we will move forward. We'll do I++, right? So we won't be visiting this index now. So there's no need of updating in the index of 1. If you want, you can do, that's no harm, but that is not required, right? So before swapping, let's update the new position in the map of this 5, right? So for that, what you will do, that in the positions map, for the element original of I, make it to current position, right? So the position of 5 will now be updated to 3, right? And then we will do swap in the original array the index I and the index current position, right? This is what we can do, right? So now what will happen? 5 and 1 will be swapped, right? And your number of swaps will become 1 now. And similarly, then you will move to the next element. I will become 1. Again, these are not matching, so it will come inside. Swaps will be increased by 1, so this will become 2. Now, what is the current position of the target element? So the target element is 2, its current position is 2, so 1 and 2, these indices are going to swap, right? So in current position we will have 2. So now in the map for 3, the position will be updated to 2, right? And these two will be swapped. So this is what it will look like. Then I will become 2 will come here. Now these are same, so it will not go inside this. Then I will become 3. Now these are not same, so it will go inside the if condition. Swaps will be increased by 1. Then we will identify what is the current position of the target element. That is what is the position of 4. So it is 4. So in current position we will have 4. Right? So in this original element, that is 5, we will update its position to 4 now. So this will be updated to 4, and 4 and 5 will be swapped, right? Then I will become 4. Now these are already matching. It will not go inside the if condition. So now I will become 5 and the loop will stop there, and we have the total number of swaps required. So with this approach, for each level in our binary tree, we can identify how many swaps are required, and then we can sum up all those swaps, and we will be able to identify the total swaps required for sorting each level's node values in our binary tree. So let's quickly code this out. So first of all, let's create a queue for performing BFS. This will store our tree node. Let's name it queue. In this queue, we will push our root node initially, right? And then we need a variable total, which will denote how many total number of swaps are required for sorting each level's node values, right? Now we will perform our BFS, that while our queue is not empty, what do? First, take the size of the queue, right? So in size, we will store the size of the queue. And then we also need a vector for storing all the values of the current level, right? So let's name it level values. And we already know the size, so we can give the size as well, right? Now we are going to run a for loop that int I equals to 0, I less than size, I plus plus, right? Inside this, what you will do, you will take the front node from the queue, right? So this will give you a node which is present in queue dot front, and then we will pop it from our queue, right? Once you have done this, let's update it in our level values vector. So in our level values vector, at the index I, we can keep the value of this node, right? We could also create level values vector over here without giving the size, and we can do pushback over here. So That is also what we can do. Now, once we have updated it inside our vector, now we need to push the left and right child if they exist inside the queue for the next level, right? So if nodes left is not equals to a null pointer, then in the queue, push the nodes left, right? Then if nodes right is not equals to a null pointer, then in the queue, push nodes right, right? And then here in our total, we can add how many swaps are required for sorting this particular level values, right? So for that, we can create a function, let's suppose get swaps, and in that, we are just going to pass our vector, which is level values, right? This will give us how many swaps are required, and at the end, we can return this total, right? See, once we are done with this for loop, in our level values, we will be having all the values which are present at the current level, right? So we can simply give it to some function which takes an array as an argument and tells us how many swaps are required in sorting that array, right? So now let's create this function. So this is going to return us an integer. Its name will be get swaps, right? And it will receive a vector. Let's name it original, right? Now we can declare a variable swaps where we will be counting how many swaps are required, and then we also need the sorted version of the array, right? So we'll create another vector. Let's name it target, and in this we will store the original, right? And then we can sort this target. So sort target dot begin comma target dot end, right? So now that we have done this, we also need a map for storing the indices, right? So we can create an unordered map. We don't want the keys to be sorted or something. So unordered map will work for us. Let's name it positions, right? Now we need to first update the original indices of all the elements in our map, right? So we'll run a for loop of I starting from 0, I less than original dot size, I plus plus, and then in our positions map for the original of I, we will update its index to I, right? So now we are done with this. Now let's find out how many swaps are required. So we'll run a for loop again for I less than original dot size and I plus plus. Now inside this, we'll check that if the original of I is not equals to the target of I, then that means a swap is required. So we will increment the number of swaps by 1. Then we'll take the current position of the target element. So this will be positions in target of I. Then we will update the index of the element present in the original vector in our map, right? So in positions for the original of I, we will update its index to current position, right? And then we can just swap original of I and original of current position, right? And here we can return the swaps required, right? So with this, we will be able to solve our problem. So time complexity wise, we are performing a BFS traversal over here, right? Which will visit each node exactly once, right? So that will contribute order of n time, right? And then at each level, we are performing the sorting of the values at that particular level, right? Now, sorting will take, if let's suppose the number of nodes in that particular level is x, right? So it will take x log x time in sorting, right? So in the worst case, when your tree is complete binary tree, right? In that case, what will be x? It will be n by 2, right? Where n are the total number of nodes in the entire binary tree, right? So basically, your complexity will be somewhere around order of n plus order of n log n, and we can write it as order of n log n, right? And then space complexity wise, we have used a queue for performing our BFS, right? Which will store the nodes at a particular level. So whichever level will be having the maximum number of nodes, that will be the maximum number of nodes that will be present in the queue. And then we have also created a level values vector, right? And that will also store the nodes which are present at any particular level, right? And then we have also here taken a target vector, right? This target and original will also have the nodes at a particular level, right? So in a worst case, when we have a complete binary tree, it will be n by 2, right? So we can write it as order of n because 2 is constant, right? So this will be our space complexity. So let's run this. So our test cases are accepted. Let's submit this. So it got accepted. Thank you so much for watching. Please like the video and subscribe our channel.